we will now look at the next unit as far as this course is concerned, and this unit is called junctions. Okay, and by junctions we mean the merger of two different materials, okay, which could be a semiconductor and a metal, or a metal and a metal, or two different semiconductors. Okay, and in particular we want to look at what happens. We will use all the concepts we have established so far in the fundamentals of semiconductors, and we will use those ideas to see how materials would behave when they are adjoined to another material. Okay, and it gives you a lot of interesting physics and some interesting ideas for engineering. So in high school I think several of you might have heard of p-n junctions. So p-n junctions is one kind of a junction, but we will be looking at metal semiconductor junctions, p-n junctions, junctions caused to create other devices such as transistors, etc., etc. And the purpose of this lecture is to establish some very key ideas, some very key concepts that we will be using time and again when we want to analyze and understand how junctions behave. Okay. So the first concept has got to do with drawing something called as a band bending diagram. Now this is a very useful idea. Okay, it is really not compulsory or necessary, but it is a very nice graphical representation of what happens near a junction, okay, and how the semiconductors or the materials involved will be influenced by the creation of such a junction. Again we will try to understand what band bending means. We will work out some examples and we will get those concepts clear, but before that let us try to look at some of the properties of different materials. So let us say we are trying to create a junction between say semiconductor 1 and semiconductor 2. Okay, so we have these two semiconductors separately initially. Okay, we know how they behave with thermal equilibrium, we know how they behave if we throw light on it, we know how they behave if you establish a current, if you establish a voltage across it, etc. So we have studied all this with respect to a semiconductor and thermal equilibrium and a non-equilibrium, but now what we are trying to do is see what happens when you bring these two semiconductors in contact with each other. Okay, and this is what is called as the junction between the two semiconductors. We want to see what happens to what is the physics in and around the junction. So before we establish all these concepts, let us look at some of the key properties. Okay, so there are some pointers. Okay, so I have just labeled these out as key pointers, and we will just go through these aspects one by one, and these aspects will get more and more, you will familiarize yourself with these aspects as we go through this course, okay, as you solve out more examples. So the first thing is, let us take a semiconductor. So you are all familiar with the conduction band edge, the valence band edge, and the location of a Fermi level. The semiconductor will also have an intrinsic Fermi level position, which is the Fermi level when the semiconductor is pure. But here, as you can see, the Fermi level is offset and it is closer to the conduction band, which is indicative of the fact that the semiconductor has been doped n type. Okay. So nevertheless, for any semiconductor, you have your valence band, you have your Fermi level, and you have your conduction band. Now we define a reference energy level called as E vacuum, the vacuum energy level. Okay, it is just a reference energy level, and we establish two terms. Okay, the first is called as the work function, which is a term which many of you might have heard with respect to metals and with respect to the photoelectric effect. It is the same work function that we are talking about, and something called as the electron affinity, okay, which I think students from chemistry might be more familiar with. So we have the work function as being the difference between the vacuum energy level and the Fermi level, okay, of the semiconductor. Okay, and we typically represent the work function by this symbol phi, the Greek alphabet phi, and for a semiconductor I will use the subscript S, and for a metal I will use the subscript M. Now phi is the potential, and the energy is simply Q times phi. Okay. So if you know this potential as say, so if you know the energy in terms of let us say the Q phi is equal to say 0.1 electron volt, it simply means phi is 0.1 volt. Okay. So the energy and potential are easily related in any picture like this by simply multiplying the potential with the charge. So the energy level, the energy difference between the vacuum energy level and the Fermi level is essentially the work function of the semiconductor, and the difference between the vacuum level and the conduction band edge is the electron affinity of the semiconductor, and we will represent the electron affinity by the symbol, I think it is called chi, and for a semiconductor we will say with the subscript S. So now for a metal, okay, so in the case of a semiconductor you must always remember that the electron affinity is always a constant, it is a material property. So you can engineer the device in any manner you like, you can apply whatever voltage you like, we can play around with the engineering as much as we want, but the electron affinity is always a constant. So you cannot really change this energy difference between the vacuum energy level and the conduction band edge. So that is a useful pointer to remember, which is that the electron affinity for a semiconductor is fixed. Now in the case of a metal, so just before we head to a metal, what about the work function of a semiconductor? Is that fixed? Clearly the work function of a semiconductor is quite variable because it depends upon the doping, right. If I dope it p type, I have changed my work function, and if I dope it slightly more n type, I have moved the Fermi level closer to the conduction band edge and my work function has changed. Okay. So the work function for a semiconductor really is not a constant, whereas the electron affinity is a constant. Okay. Now for a metal, the metal does not have a conduction band edge and a valence band edge, instead a metal just has the Fermi level, and the work function for a metal is the energy required to take the electron from the Fermi level and into vacuum. Okay. So it is again the difference between the vacuum energy level and the Fermi level of the metal. But for a metal, the work function of a metal is a constant. Okay. So in other words, for a semiconductor the electron affinity is a constant, and for a metal the work function is a constant. The work function for a semiconductor depends upon the doping. So if these pictures are clear, then you are one step closer to drawing a band diagram. Okay, and I will show you what a band diagram is and how we can draw it. So essentially what do you mean by a band diagram? So what we are trying to see is if you bring two different materials closer and create a junction between these two materials. So you create a junction between these two materials, it is very possible that you have carrier movement across the junction simply because the Fermi levels are not aligned. Okay. So you can think of it this way. So if you remember a while back I had used the water bucket analogy, okay, and I told you that the analogy is helpful, but it is not really going to take you all the way. Okay, but let us get back to that, it is going to help us a bit here. So, let us say you have two buckets, okay, and you have water filled till different levels in these two buckets. Now, we had already discussed, the water molecules above this level do have a Boltzmann's distribution, and therefore, we are quite we are quite close to what the Fermi level in a semiconductor is, using this little picture here. So, you have a lot of water molecules here, you have plenty of water molecules below the Fermi level here, and this was the Fermi level for this bucket, and this is the Fermi level for the other bucket. Now, while creating a junction, what we do is we bring these two buckets close to each other and we simply remove the edge between them. Okay, there is no wall between these two buckets. So, what's going to happen? So, what will happen is the water molecules will not like to see these two different levels. There is clearly a concentration gradient here, and therefore, you will establish a diffusion of electrons, or in this case water molecules, from the bucket that has got a higher water level to the bucket that has got a lower water level. So, the electrons or the water molecules will flow out till the water level is the same in both buckets. Okay, so, in this case water molecules have transferred from there to here in order to align, or in order to make the water level the same. You will not end up in equilibrium, you will not end up in a situation where there is a difference in the water level in space. Okay, so, the water will flow and it will ensure that the level which was equivalent to a Fermi level is constant throughout this region. Okay. A similar thing happens here. Okay. So, here too we will have a Fermi level alignment, and if you create a junction between two different materials, the Fermi level tells you is an indicator of the energy at which the probability of you finding an electron is half, electron occupying a state is half. Okay. So, that probability is half at this point for this material, and that probability is half for that point of that material, which in some sense implies that there are larger number of electrons sitting here as compared to this material. And just like in the case of a bucket with water, if you bring these two materials together and you create a good junction, which means very nicely getting rid of any edge between them. Okay. Okay, so do not take that previous statement extremely literally. So, what the way junctions are created is through a very different process, and it is not equivalent to you removing the wall between two buckets. So, please do not take that statement too literally. So, if you were to create a good junction, then the electrons will flow from the material having a higher Fermi level to the material having a lower Fermi level. Okay, which means the material having a lower work function to a material having a higher work function. So, what do you mean by band bending diagram? It is that we want to see what happens to the conduction band, valence band and Fermi levels of the two materials when you create a junction. So, when I create a junction, we will have electrons moving back and forth, and electrons moving from one material to another, and these bands might change their location. Okay, they may not want to be where they are right now. Okay, and that is what we want to look at in a more quantitative manner. So, that is what we mean by band bending, and I'll soon bring up an example, so those things will become clear. So, the first point in order to understand what happens to the conduction band edge, valence band edge and the Fermi level is to note that the Fermi levels will align the moment you create a junction. That is the first point. The second point is something that we have already discussed, which is the work function for a metal will always be a constant, and the electron affinity for a semiconductor will always be a constant. Okay. So, these two will not change. So, remember that. And the next thing is very far away from the junction. So, let us say you have a very long piece of material 1 and you have another long piece of material 2 and you created a junction. Okay. So, these are long and we can soon define the length scales more accurately, but we create a junction between these two materials. Now, you have a lot of interesting things happening in and around the junction. Okay. You have the bands moving, shifting away from where they were, you have electrons moving across, etc., etc. But very far away from the junction, okay, the material really does not see any of these any of this phenomena. Okay. And very far away from the junction, the material could be said to live in its own world and retain the properties that it had if it were to be in equilibrium. If the entire system is in equilibrium, then the material really does not see any change, okay, and very far from the junction nothing interesting happens. So, then while drawing a band bending diagram, we watch for how the electrons move about. So, this is exactly what I described with the water bucket analogy, okay, which is to see which material transfers electrons, okay, and that will help us gauge the bending of the bands in a semiconductor. Finally, in order to analyze the degree of bending and the shape of bending and what the electric fields are and what the potentials are inside a junction, we solve Gauss's law, and we solve the differential form of Gauss's law, which is something called as the Poisson's equation. Okay, so these are several pointers that I have thrown out quite early, okay, and these are things to remember, and we will discuss each of these in the next few minutes, and we will soon see how to how these can be used to draw a band diagram. Okay. So, let us go to the very first point, which was the alignment of the Fermi level. Okay. So, I stated that I gave this analogy of the water bucket, okay, the bucket carrying water. So, one bucket had a different level, the other bucket had a had water at a much shallower level, okay, and when we created a junction, we just removed the wall separating these two, and we said that the level of the water would align. And this was sort of built upon the use of this analogy a while back when we were discussing the Fermi function and the Boltzmann's distribution, etc. But now let us try to mathematically prove this, the alignment of the Fermi level. Okay, so let us take two different materials. Let us say there is material 1 and there is material 2, and let us say material 1 has got some density of states which is given by G1, and material 2 has got a density of states given by G2, and depending upon the location of the Fermi level. Okay, so, this material 1 has got a Fermi level located at EF1 and material 2 has got a Fermi level located at EF2, and depending upon the location of this Fermi level, material 1 could have a Fermi function called F1 and material 2 will have a Fermi function F2. So, F1 would be something like 1 by 1 plus e to the power e minus EF1 by kT, and F2 would be of the form 1 by 1 plus e to the power e minus EF2 by kT. And to continue on, let us say there are N1 free electrons in material 1 and N2 free electrons in material 2 and P1 vacancies in material 1 and P2 vacancies in material 2. And now what we do is we are trying to bring these two, we try to bring these two materials together and form a junction. So, before we do that, let us try to get a gauge on what are N1 and P1. So, what is N1? N1 is calculated from the probability of occupancy of all these states in material 1. So, it is F1 G1 and N2 is F2 G2. And what is the probability of non occupancy, that is the probability of finding holes? It is 1 minus F1 G1, and in material 2 it is 1 minus F2 G2. So, these are the parameters that we have in material 1 and material 2. So, now let us say that we try to create a junction between these two. Now, we bring material 1 and material 2 together and we have established a junction. Now, at thermal equilibrium, so we created this junction and we left it in dark, we did not apply a voltage, we did not apply light, we left these two materials with the junction in the dark. Okay. And what would happen? In the dark there cannot be any current, okay, you can't have current. If you have a current, you can establish, you can do work, and you have probably solved the energy crisis. So, in the dark, any flux across the junction, so let us call that the junction, okay, so between these two materials, that is 1, that is 2. Any flux from left to right across this junction should be matched by a flux of carriers from right to left across this junction. Okay. These two should be the same, otherwise you will have an effective current. So, what does the flux from left to right depend on? It depends upon the number of electrons I have in material 1 and the number of vacancies I have in material 2. Because if there are no electrons in material 1, there is no current from material 1 to material 2. And even though there are electrons in material 1, if there are no vacancies in material 2, the electrons cannot fill any states in material 2, and therefore, there will not be any current. Okay. So, the current from 1 to 2 depends upon N1 and N2. In fact, it is the product. So, if I want to match the flux from left to right depends upon this product N1 P2, and the flux from right to left depends upon the product N2 P1. So, you need to have electrons from the second material trying to occupy the vacancies in the first material. So, at thermal equilibrium there cannot be a current, and therefore, these two fluxes must balance each other, and N1 P2 must be equal to N2 P1. So, let us write out N1 and P2 in terms of the density of states and the Fermi functions using these terms that we described here. So, N1 is F1 G1 and P2 is 1 minus F2 G2 and so on and so forth. And if you were to solve this equation out, you will find that it says that F1 is equal to F2, and F1 equals to F2 automatically implies that at thermal equilibrium EF1 will be equal to EF2. So, in other words, if you were to create a junction between these two materials and keep this system at thermal equilibrium, the Fermi levels will align and EF1 will have to be equal to EF2. Okay. So, this is a little hand wavy proof that the Fermi levels of these two materials will align when you create a junction. So, now let us start creating a band bending diagram. Okay. So, this is a very useful concept as I told you, and I think it is best done with the help of an example. And I will create a band diagram for I will consider two examples because we will very soon be using these examples. So, you might as well just take this opportunity to consider these two cases. Okay. So, the first band bending diagram will be for a junction created with a metal and an N type semiconductor. So, you have a metal that is going to form a junction with an N type semiconductor. Okay. And we will choose this particular condition that the work function of the metal, okay, so Q phi m, so this is all, if you consider everything in terms of energy, so it is all got a Q there, and phi m is simply the potential. So, Q phi m is the work function of the metal, is greater than Q phi s. What does that mean? It means that the Fermi level of the metal is lying further away from the vacuum energy level as compared to the Fermi level of the semiconductor. So, the Fermi level of the semiconductor is closer to the vacuum energy as compared to the Fermi level of the metal, or in other words, the semiconductor has got a Fermi level that lies above the Fermi level of the metal, okay. And it is a semiconductor that is going to donate electrons to the metal if we create a junction, because that is what we looked at in the water analogy. Okay. So, this is the condition. So, the first thing we need to make sure is if we create a junction, the Fermi levels will align, and the second thing to make sure is that the work function of the metal does not change and the electron affinity of the semiconductor does not change. Okay. So, let us say we create a junction between these two materials. So, the first thing we do is let us align the Fermi level, we keep the Fermi level flat. Okay, so, you can see that the metal and the semiconductor now have the same Fermi level. So, we are all at thermal equilibrium. Okay. So, all at thermal equilibrium. So, if we go out of equilibrium, the Fermi levels need not be aligned, because then there is no reason for the flux from the left to the right to be matching the flux from the right to the left. So, it is all at thermal equilibrium. So, the moment you have a metal n type semiconductor junction with phi m greater than phi s, the Fermi level will align, the vacuum level will adjust itself so as to ensure that the electron affinity in the semiconductor and the work function of the metal is always a constant. So, you can see the work function of the metal has never changed, the work function is the same. Okay. The difference between the Fermi level in the metal and the vacuum level is constant throughout. But since the semiconductor had a higher Fermi level as compared to the metal, the semiconductor will now donate electrons to the metal. Okay. So, you will have in a metal semiconductor junction with phi m greater than phi s. Okay. So, you had an n type semiconductor, you have a metal here, and you have an n type semiconductor, and it had a Fermi level that was located higher as compared to that of the that of the metal, and electrons will effectively flow from the semiconductor to the metal upon the creation of a junction. So, what do you mean by electrons are going to flow from the semiconductor to the metal? So, let us look at close to the junction, let us look at this region close to the junction. So, the semiconductor has now lost electrons. Okay. So, it initially had the equilibrium electron concentration, it had some NO which was approximately ND, and now the semiconductor has lost electrons because it has donated it to the metal in order to align the Fermi levels. So, if the semiconductor has lost electrons, it implies that the conduction band has moved away from the Fermi level position, because what is the electron count? The electron concentration is Nc e to the power minus Ec minus Ef by kT. So, now as this electron concentration goes down, the Ec minus Ef must increase. Okay. So, therefore, since this region has got fewer electrons as compared to the bulk, okay, so this is the bulk region very far away from the interface, the conduction band edge will move away from the Fermi level. Okay. So, it is no longer going to retain its position here, close to this it is going to move far away, and then just a little after that it is going to be located there and there and there, and therefore, you have a gradual bending of the conduction band edge with respect to this Fermi level. Now, the energy gap between the semiconductor has not changed. Okay. So, therefore, the valence band edge will also move in accordance. Now, very far from the junction, okay, so let us look at this region. there is no change here. It is as though you had a pristine semiconductor, right. You look at this condition here and this condition here. You still have an n type semiconductor. So, this is the EC minus EF. It is n doped because the EF is lying above mid gap. That is your band gap, that is your EV, EC, EF, and that is your E vacuum with the electron affinity being constant. So, nothing has happened. This region far away from this junction has not really seen anything interesting, but it is only close to the junction that we have lost some electrons. And as you move deeper, as you start walking from the junction and into the semiconductor, as you get deeper and deeper, you will find that the movement of the conduction band away from the Fermi level is sort of gradually decreased till you reach a point where you are in the bulk. Okay, so, this region here is called as the bulk. It is a region that has not seen anything interesting because it is too far away from the junction, and it is only this region here that is influenced by the creation, the formation of a junction. So, some simple ideas. We will again come back to drawing a band bending diagram when we talk about metal semiconductor junctions. And throughout the vacuum level, as I mentioned, it adjusts itself, okay, so as to keep the electron affinity constant and the work function of the metal constant. Okay. But note here that the work function of the semiconductor need not be constant, okay, and it is not required. Okay, so, this is the way you construct a band bending diagram. So, essentially what we do is you first align the Fermi levels and you just mark out which of the materials is going to donate electrons. Where is the electron going to flow from? Is it from the right to the left or left to the right? And depending upon which material has lost electrons and which material has gained electrons, we adjust the band position, the EC minus EF location in these two materials, okay, and therefore you get a bending of the bands in space. So, this is a energy distance diagram. So, the x axis is distance, the y axis is energy, and it is also indicative of potential. So, if you want to locate the potential difference between these 2 points, it is simply the energy difference between those 2 points divided by q. So, that is the potential difference. Okay, now, several other points. Okay, now, the band bending diagram is always drawn with respect to electrons, okay, and what I mean by that is if you see a slope here. So, for example, if you see for example, let us take this region here, okay, you see this bending of the bands, you see the bending of the conduction band. Essentially what this means is that the region that is lower, located at lower energies, have got a higher potential, okay, as compared to the regions located at higher energies. So, if I have a Fermi level and I increase the potential of that, so let us say there is a metal and there is a Fermi level here, and I increase the potential of the metal, I increase the voltage, the Fermi level will start moving downward, okay. And therefore, since this is the case, if I have an electron and a hole, okay, the electrons will like to run down the hill when you see a bending, and the holes will like to run up the hill, okay. So, this gives you a very intuitive feel for what the electrons will do and what the holes would do, okay. Now, since it is an n type semiconductor, there are not many holes, there are very few, and whatever majority electrons were there have all moved in here into the metal, and essentially any electron coming in here will try to run down the hill and away from the junction. So, there are going to be very few electrons here and very few holes here. Therefore, in some sense this junction can be said to be sort of depleted of free carriers, okay. So, we will come back to these points later. So, this is the way you draw a band bending diagram, and that is the way you look at the different aspects of it. So, just to complete this, let us go do another example. So, let us take a p type semiconductor and an n-type semiconductor. And let us try to create a junction. So, this is your very well known p-n junction, okay. It is the same semiconductor. So, here that is my electron affinity, that has to be constant. Again, if you want the energies, it is q times chi, and the Fermi level for a p-type semiconductor is located closer to the valence band edge, and the Fermi level for an n-type semiconductor is located closer to the conduction band edge, and here you have your two different semiconductors. And now we try to create a junction. So, let us try to think about what will happen before we actually see the next figure. The first thing is the Fermi levels will align, okay. So, let us align the Fermi levels. Now, which material do you think will donate the electrons to the other? So, the Fermi level here is higher than the Fermi level in a p-type, okay. So, it is very likely that the electrons will flow from the n-type into the p-type once we create a junction. So, if the electrons flow from the n-type and into the p-type, what do you think will happen to the conduction band edge and with respect to the Fermi level in the n-type material? So, since the region near the junction will lose electrons, the conduction band will have to move away from the Fermi level position, okay. So, in the n-type material, so this is the Fermi level, that is the junction. It is expected that the conduction band edge move away from the Fermi level position. And in the p-type material, the p-type material has now received electrons, okay. It had a small number of electrons initially, but now it has received a lot of electrons from the n-type material. These electrons have all diffused in from the n-type material, and therefore, this region near the junction has now got excess electrons, and therefore, the conduction band would like to move closer to the Fermi level in order to reduce the EC minus EF gap, and therefore, the p-type material will see a band bending that looks like that, where the Fermi level sort of bends downward, where the conduction band bends downward to meet the Fermi level in the p-type material. Therefore, we can construct a band diagram that looks like this. So, you can see that the conduction band edge has moved away from the Fermi level in the n-type, and it has moved towards the Fermi level in the p-type, therefore, giving you a band bending that looks like what is shown, okay. So, this is the method to construct the band diagram. So, throughout you will find that the electron affinity is always constant. So, the final point before we stop this study of this overview of junctions and actually start looking at some certain very specific junctions, is to understand something called as a Poisson's equation, okay. Now, we did draw all this band bending, okay. So, let us say it was a p-type and an n-type semiconductor. We said that the band bending would look like that. The question now is, how do we exactly and very quantitatively determine the shape of this bending? What is this? Okay, so that is x. So, what is the relation between the potential and the electric field, etc., with respect to as a function of x? So, we want to establish this quantitatively. We want to know the exact shape of this bending, because these quantitative results can help us estimate many things such as currents and charge concentrations, etc., in a more accurate manner. So, in order to establish this, get this quantitative estimate of the amount of bending, we need to solve Gauss's law, okay, and we want to particularly solve the differential form of Gauss's law, okay. We use the differential form of Gauss's law, which is something called as a Poisson's equation, and here is a very brief understanding of that. So, Poisson's equation simply says that the change of the electric field in space, so this is the one dimensional Poisson's equation, is simply equal to the charge concentration per unit volume, okay. So, this is the charge per unit volume, okay. It is not per unit area, it is not the total charge, the charge per unit volume divided by the permittivity of the material, in which we are doing all this analysis. So, in our case it is mostly going to be the permittivity of the semiconductor. So, that is the electric field, that is the distance, that is the spatial coordinate x, rho is the charge concentration per unit volume, and epsilon is the permittivity. And since the electric field is minus d phi by dx, which is where phi is the potential, okay, we can also rewrite Poisson's equation as d square phi by dx square is equal to minus rho by epsilon. And this is a relation that we will use, and we will look at some examples soon on in order to establish the correct nature of the bending of bands. Okay. With that, we will close our overview on how to create what a junction does and how to create a band bending diagram, and what the Poisson's equation is. And we will now start looking at very specific junctions, and of interest are the metal semiconductor junction and the p-n junction, and we will start looking at these junctions in order to establish our understanding of the different semiconductor devices.